All right, I'm gonna deal with more op-amp examples. Okay, so we talked about the last basically two lectures about this idea of amplification, right? So if I have this is sort of the picture that we draw at high level for these things. So I have an input voltage, and we'll deal with voltage to voltage. You can have amplifiers that amplify current. You can have amplifiers that amplify power. We're going to deal with these types of voltage, most common type of thing to worry about. We talk about the gain. The gain doesn't, there's nothing special about the letter A for the gain. You see different values, but oftentimes it's A. All right. And it's the ratio of the output voltage over the input voltage. Typically, the output voltage, because it's an amplifier, is bigger than what the input voltage is. I guess it could be smaller, but typically it's bigger. Okay. All right. So all these circuits are used for that sort of thing. So we talked about the op-amp model here. So basically we said, I showed it. It's basically all a bunch of transistors all sort of slapped together inside this thing. And I've got this model for that transistor thing, right? Which is basically there's an input resistance, R sub I. There's an output resistance, R sub O, and then there's this dependent source, A times the difference between V plus and V minus. And I said that V plus and V minus are the node voltages for the two inputs. V plus is at the input labeled plus, V minus is at the input labeled minus, okay? All right, so we said this is the general form of these things, and all of these guys have parameters Ri, which is said the input resistance, Ro, which is the output resistance, and A, which is the gain. All right, so R sub I, what value does that kind of take on, did we say? Each of these three things here, what values did they kind of take? How about A, the gain? We talked a lot about that last time. What's the value of that gain? We basically said that gain is super large, right? We said we approximate it to be infinite. All right. The output resistance there, 0. And the input resistance, basically what? Infinite. If that input resistance was infinite, we said, what's that mean about I plus and I minus, which I've defined to be the two currents going into the plus terminal and the minus terminal. They're equal to each other and they're equal to 0. Now, V plus and V minus, what about them? Well, we basically showed that because the gain is so big and because of the way we operate these things, it's always true that V plus and V minus are approximately equal to each other. Not necessarily 0, but approximately equal to each other. And so that led to, we kind of derived out these two rules here. The first one is no current flows into the input terminals. All right, comes from the fact that this guy is infinite input impedance. And the use of what we call negative feedback leads to the second golden rule, which is the input terminals always have the same voltage. All right, now I added here something that's really critical. To use these things, there's always a connection from the negative input terminal to the output terminal. There has to be. All right, that is what makes the negative feedback. All right, we're not going to get into a deep analysis of that, and I'm not going to give you some trick circuit where it's not like that. All right, but that is a critical thing that always has to happen in these circuits, is there has to be a connection like that. Okay. All right, so I want to look at a couple of more examples today, and I don't necessarily want to take a whole lot of time today. I might cut it a little bit short in case anybody wants to come up with some questions, but I do want to do a couple of examples. So I've got this circuit here. All right, now, oftentimes in all of these things, they just label the nodes with these things. All right, so what I have here, let's say I put a voltage source V in, like this. V in of T, and I want to measure V out of T. All right, so those are node voltages like that. How would I approach a problem like this one? There's no resistors, nothing in the circuit, no resistors, no capacitors. Looks like it should be simple. Let's see if it is. Where do I start with any of these problems? Finding voltages. Okay. So what do we know? We start with our golden rules anytime I have one of these. So what are my rules? Well, so I have I plus here. I have I minus here. What do I know about those two things? They're equal to 0. I plus equals I minus equals 0. What do I know about V plus and V minus? They're equal to each other. Okay. So V plus is the node voltage right here. So if I define for myself, this is V plus, V minus is the node voltage at the other guy. I don't think I have enough space to write that in there. V plus and V minus are equal to each other. And what are they equal to? V in. Okay. Definitely the case that V plus is equal to V in. Looking at this circuit, V minus is also equal to something, isn't it? Well, it's equal to V in, right? This is because of the golden rule, right? So just to be clear, V plus equals V minus because of the golden rule, all right? For the circuit, V in equals V plus, right? This part comes from the circuit right here. What about V minus? What's it equal to? It's equal to V out. So if I combine those three statements there, what does that tell me? If I combine those things, I get that V in equals V out. So what's the gain of this guy? The gain is 1. So this is a voltage follower, sometimes called a buffer. Very easy circuit to analyze. Is it a stupid circuit? Seems kind of stupid, right? I put input voltage and I have an output voltage. They're equal to each other. Why would you ever build this thing?
Then a certain voltage at a certain spike rate, circuit.
Yeah, that's a good thought. Yeah, if I had basically the same voltage at different points in the circuit. So a place where I've used these pretty commonly is, let's say I have like the example I gave where I'm building a system and I've got a sensor. Okay. So if I said I had a sensor of sorts, common thing to do, I don't know, give me an example of a sensor. One example of a sensor might be, let's say let's say I had a thermocouple. What's a thermocouple do? A thermocouple measures the temperature, right? It's a wire with two dissimilar metals. If I take two dissimilar metals, weld them together, and connect that joint to another object, I can measure the temperature of that object. All right, this guy is basically two wires connected together. All right. Now, if I use this thing in the real world, I'll get a voltage from this thing that is proportional to the temperature. But looking into the terminals here, what do I have looking into the terminals? Well, I got two pieces of wire. Somehow there's going to be a voltage at those two pieces of wire. But if I got two pieces of wire, what must I also have here? Resistance. So I have a Thevenin equivalent looking into there, right? So if I think about this, I got a Thevenin equivalent that I could draw. Let me not do it. I'll do it this way. Basically, it would look like this. Electrically, looking into those terminals, over there, that device on the left, what I have looking into those terminals is a voltage source in series with some resistance, okay? Let's say I wanted to measure that voltage, right? What I care about is this V open circuit, right? This V open circuit is proportional to temperature, let's say, all right? If I want to measure that value, if I hook it up to, let's say, something with a resistance, then I'm not actually measuring VOC, am I? I'm actually measuring VOC minus whatever drop I have in that resistance. But what if I did this and I said, all right, what I'm going to do is I'm going to hook it up to a voltage follower like this, right? What would that do? How much current now flows through here? 0, right? So what would the voltage here be? VOC, no matter what. So that type of device, that's why, so we use that idea of like the Thevenin equivalent a lot to be able to think about interfacing with real systems, right? I said I use it if I'm designing, you know, a power system for a building. or if I'm designing, you know, sort of a sensor interface or something like that, I always think about if I have a device that I'm connecting up to, that device has some open circuit voltage and some resistance, right? Or impedance more generally, right? And this guy basically just creates a wall there, if you will, so I don't have any current flow. So it looks like a goofy circuit the first time you see it, but it turns out to be a pretty useful thing to have, okay? All right, this is one that we sort of did the other day, but I want to look at this one again, all right? And we're going to look at a couple of versions of this one. The inverting amplifier, right? So let's say I took a voltage source here, like that, called that VS. And then I have V out. So I want to figure out the gain again, all right? So what would be my approach here? Well, I start with the golden rules. One is that I plus equals I minus equals 0. The other one is what? V plus equals V minus. Now the question is, usually at that point I say, well, I look at the circuit and I say, one of those two things I can probably usually tell from looking at the circuit. In this case, which one of those can I tell? V plus is what? V plus is 0. So from the circuit, I can see that V plus equals 0. So that tells me that that's equal to V minus. All right. So effectively what that means is that this point right here is also grounded. There is not really a connection. Sometimes we call that a virtual ground because it's virtually grounded by the fact that those 2 points have to be equal to each other. All right, so we also know I plus and I minus is 0. So that means here's I plus. Where's I minus? Well, I minus is here. The current into the minus terminal. To solve this thing, I got to do what? You got to do node analysis. And the node that I worry about basically is right here. All right. So I'd call this I1. I'd call this I2. And what I do is I write the voltages across here. I usually write them like that. Okay. So again, I do the way I do nodal analysis, which is slow, right? So the way that I do this is I would say, I'd write it in terms of the current. I1 goes in. Any other currents going into that node? No. So I1 equals what? I2 plus I minus. Now we know I minus is 0. All right. So I'm basically left with I1 equals I2. Okay. So I1. So the way I define that is I'm going to call that, all right, I'm going to call the voltage across here V1 and the voltage across here V2. So I say V1 divided by R1 equals V2 divided by R2. Okay. So I wrote it, I basically, what I did in going from this step to this step is what? What did I do? Is this node voltages? It's not, right? What did I write from going from this step to this step? What did I use to go from there to there? Yeah, I used Ohm's law, right? I said I equals V over R. Okay. So I'm left with that. Then I got to put those in terms of the node voltages. So what I do with that is I say, what's the node voltage at the plus terminal? What's the node voltage at the minus terminal? And I do that for each of them. So for V1 here, for this guy here, what's the node voltage at the plus terminal? Yes. All right. What's the node voltage at the negative terminal? 0. All right. What about V2? What's the node voltage at the plus terminal? 0. What's the node voltage at the negative terminal? V out. Okay. Over R2. So basically what I end up with is, if I'm wondering about the gain, it's V out over VS equals negative R2 over R1. Okay. Then there's a whole, you go online, you'll find there's a whole smorgasbord of these circuits, inverting, non-inverting, there's all sorts of types of these things. And you could look up the gains of all of them, right? There's no need to memorize them. All right. It's not a quiz show. I'm not going to ask you to do that, but I will you know, sort of expect that you should be able to do the nodal analysis to write this stuff out. Okay. All right. You guys follow where we get that? All right. Now we say what this typically is, you know, if I want to get a gain of 10, typical design problem would be, okay, I want to get a gain of 10. So what do? I got to choose what resistors I need to get a gain of 10, right? Or a gain of 9 or whatever, right? So what would you do to do that? You got two unknowns. So how do you do that? Pick one and guess the other. No, you know, so if I wanted to get a gain of 10, I could pick R2 as 10 ohms and R1 is 1 ohm. Now you'll notice in my examples, I always choose things that are in the kilo ohms. All right. The reason I do that is if I had 10 volts out of this thing and I had like 1 ohm resistors, I'd be having like 10 amps coming out of this. Op amps are not meant to give you that kind of current. I know that you don't, right? So I won't ask you to do design on any sorts of things, but that's typically what we end up doing is you go in like junior design or something like that, you're going to be designing, you know, sensor circuits and things like that. And you would actually sort of choose these values. And you'll learn more about these circuits later, right? But the typical values are not like on the ohms level. It's usually on the kilo ohms, tens of kilo ohms level. Okay. Okay. All right. Let's look at this guy. All right. This is what I would call an integrator. All right. Now I'm going to look at this guy two ways. Why do I call him an integrator? Well, because he integrates. Okay. And so how do I look at this thing? So what I'm going to do is I'm going to say, let's say again, they typically just write the node voltages here, but let's say I add a voltage source here, V in, put it to ground, and then I have my output voltage here. Now, we're going to learn a methodology beginning next week where I sort of analyze these guys a little bit more symbolically and try to write out something more generally that I call a transfer function, all right, that relates the outputs and the inputs. But for now, I want to just deal with trying to approach this guy from just regular circuit analysis. So in looking at this, I want to say for a second, I want to do this in the time domain, all right? I don't want to actually do this in the phasor domain. In other words, I want to go back to the old school way of saying I want to do it in differential equation mode. So how do I do that? Well, I can do nodal analysis still like I did before, right? So I can say I've got this is V1, this is V2, this is I2, this is I1, this is, I have I plus, and that would be I minus over there. It's not big enough to, I minus right there. Where do I start with any of this analysis? Golden rules, right? So basically I write those down for myself. I have I plus equals I minus equals 0. Let's say I have, now what about V plus and V minus? Equal to each other, not necessarily 0, right? So we write those, what I say is I always write those down. Then I go to the circuit. These are just the rules. The circuit tells me I have to figure out something about V plus and V minus. Which one does the circuit tell me in this case? V plus equals 0. All right, this is very similar to the other one that we just did. All right. So that tells me that V minus equals 0. All right, so I can do a nodal analysis again at the exact same node to get the gain relationship here, right? So I'll do it there. So how do I do the nodal analysis at that node? How do I write this? I1 equals I2. And then I got to put this in terms of, I don't know, KCL somehow, right? So how do I, or sorry, in terms of Ohm's law. So what do I say? I say, well, it's V1 divided by R. That was straightforward. What about I2? Yeah, so we know that that's got to be equal to C dV2 by dt. Okay. All right. So now what? I gotta get that in terms of the node voltages. Right, so what's V1? The voltage across the resistor. How do I define that in terms of the node voltages? What's the node voltage of the plus terminal? What's the node voltage of the negative terminal? Vn minus 0. So let's just make that guy Vn. What about the capacitor there? What's V2? Let's write V2 off to the side. What is V2 in terms of the node voltages? What's at the plus terminal? 0 minus V out. So that means that this is C times D negative V out by dt. All right. Or I can write that as Vn over RC. I'm going to write it that way. I brought the C over equals negative dV out by dt. All right. So that's going to end up being, if I wanted to get a relationship between V out and V in, the way we typically do this is to say, I don't like the way this is written because it depends on the derivative of the output. Basically, when I say, I think about a circuit, I think about I put an input into it and I get an output out of it. So I want to say, what operation do I do on the input of it to get the output? Right now, I'm doing an operation on the output. So how can I get rid of that operation on the output? I could integrate both sides here, right? So if I integrated both sides, I'm going to end up with what? What happens when what happens to the dV out by dt if I integrate both sides? The integral of a derivative is what? It's the V out, right? So basically I'm going to end up with negative 1 over RC Vn of t integral dt equals V out. All right. So I just integrated both sides of that equation to get that result. That's why I call this thing an integrator, right? What's up? Yeah, so I integrate both sides. I mean, anytime, it's just the rules of algebra, right? Whatever operation I perform on one side, I gotta do on both sides, right? So when I integrate both sides, the integral of this guy becomes negative V out. The integral of this guy becomes the integral of V in of t. Right. So you gotta perform the operation symmetrically to maintain the balance in the equation, right? So when we do that, we get that. So this is why we call this thing an integrator, right? What I'm doing here is what? I'm basically taking an input and I'm integrating it. That turns out to be a really useful thing, all right, in circuits. Why is it useful? Well, when you take controls, you'll see one of the places where that's useful. So we have sometimes, some of you guys may have heard the term before, PID, a PID controller, right? A PID sometimes. Integral, this is an integral circuit. So basically what it can do is it integrates an input. This guy turns out to be really useful in controls to guarantee that two inputs, well, this way, this becomes really useful to guarantee that a control system works properly. So that when I said, I'm trying to go 70 miles an hour in my car with cruise control, this guy guarantees that I go 70 miles an hour. Without this guy, I wouldn't be able to do it. All right. And again, that's for reasons that we don't need to get too into. All right. Now, tell me a problem I have with this circuit, potentially. Well, what would happen if V in there, what's that? If the capacitor gets charged? Well, yeah, that is, and why would the capacitor get charged? Let's say V in was like a microvolt DC, right? Even the tiniest fraction of a DC value, a nanovolt, right? If I had the tiniest little fraction of DC there at V in, let's say V in was a constant, 1 nanovolt DC, what would the output become? What's that? Yeah, so let's think about this for a second. If I took the integral, so V in 1 nanovolt constant. If I take the integral of a constant, what's the integral of a constant? A constant times T, right? So, so what would V out look like if I did that?
Negative. The N over.
Yeah, so it would be, so if I did that, yeah, it would be negative 1 nanovolt divided by RC times T. So it would just go like this. Very slowly, probably. But eventually it was so in theory, what's that guy gonna do? Where's he gonna end up? Negative infinity. Right, no, that's not possible. You can't get to negative infinity because I said the circuit is limited by how big its outputs can be, right? We said that this op amp has power supplies, a positive power supply and a negative power supply. It can't go outside of those ranges. So if you built this in the lab, what I'd do is I would see it just go like that in time. Look at an oscilloscope, it would ramp down, it would level off. Okay. So in terms of building a circuit like this, it's got its problems. Okay. But there's ways of dealing with that type of a problem, right? I can do things like occasionally discharge that capacitor, right? How would I occasionally discharge the capacitor? Put a switch on it that shorts every so often, or something like that. I mean, it's a common problem, all right, that happens. Sometimes we say we need to reset these circuits. Okay. So, and then again, it's commonly used in controls. You know, and the problem I say with this, I said even 1 nanovolt, even with 1 picovolt, 1 femtovolt, right? And no matter how small I got, eventually it would reach to infinity. All right. And the reality is I can never make the DC value on anything 0. Never, ever. Right. And it's going to be an attovolt or something, right? I mean, there's going to be something there. Okay. So it's potentially a difficult circuit to build. There's another way of looking at this thing, right? I could look at this thing in the phasor domain, right? If I did it in the phasor domain, how would I approach it now? Well, same thing. So here's Vn. All right, so I'm gonna do it phasors. I'm gonna write it like this. I'm gonna say here's Vn, and here's Vc, here's V1. All right, now nothing's changed about my golden rules, right? So my golden rules 1 and 2. What's golden rule number 1? I plus equals I minus equals 0. I'm writing that for phasors now, so I'm writing it that way. And V plus equals V minus, right? So again, those are just the rules. If I go to the circuit, which one of those do I know? Yeah, I know V plus is equal to 0. So V minus has to be equal to 0. So again, it's the same circuit, right? So what am I going to do to solve this thing? I'm going to do nodal analysis again, right? And so I go through the same process here, except I'm going to say, here's I1, here's I2, like that. And so I basically say I1 equals I2 plus I plus, or I minus. What do I know about I minus? 0. So I1 equals I2. So in this case, what I end up with is V in minus 0 over R equals V sub C over what? Z sub C. Yeah. And I'm going to write that as 1 over J omega C. Okay. 1 over J omega C. So when, let's see, what's that going to become? That's going to become, what's V sub C? Negative V out. So I have negative V out times J omega C. Like that, because I bring the J omega C upstairs. So I end up with V out over V in equals what? What would that end up being? 1 negative 1 over J omega C, like that. R. Okay. Now I just want to do a check on something here for a second. So what does this mean here? It means that the gain is a complex number, right? That's actually okay. What does that mean for the gain to be a complex number? It has a magnitude and a phase, right? So we're going to use that concept a lot in the next topic that we go through, which is going to be something called filters, right? Which is to say that I'm going to have circuits that I want to think about what they're going to do as a function of frequency. Okay. So let's think about what's going to happen here as a function of frequency. Let's say Vin was a DC source. All right. What frequency is DC? 0. Okay. So what's the gain? What's the magnitude of the gain? In negative infinity, right? So if I put 1 over 0, I get infinity. How does that match with what we said here? I said if I had a DC input would have omega equal to 0. That makes this gain infinite, right? How does that match with this?
It's the same thing as what you said earlier, that we're not.
It's just the same thing. I'm just thinking, yeah, I'm examining steady state. So once I got to steady state, you would have hit infinity. All right. Whereas here it's saying, well, it's going to ramp towards infinity. Right. Where would he get to steady state? Well, once he stopped changing. Well, where does he stop changing? Well, a long time from now. Right. It's going to basically forever from now, I guess, in reality. But in steady state, if I ever got there, it would be negative infinity. Okay. If I had any other frequency, basically it tells me here what I'm going to get. So what we're going to end up doing is sort of a concept where if I look at this and I said, all right, you guys tell me, how would I get the magnitude of this thing, the magnitude and the angle? Well, if I converted this to rectangular form, this is almost in rectangular form, but it's not quite in like A plus JB. How would I get this into like an A plus JB form? I can't have the J on the downstairs here, right? J's got to come upstairs. How do I bring the J upstairs? Yeah, so basically I end up having negative J over negative J. What's that do on the bottom? What's J times negative J? Negative J squared, which is 1, right? So this guy ends up with J over omega C R. So if I had J over omega C R, what is this saying to me? This is saying that I have, what would be the magnitude angle form of J over omega C R? What's the magnitude and what's the angle? The magnitude is 1 over omega C R, right? And the angle is 90 degrees, right? 0 plus J times something points straight up, right? 0 plus J times something, the magnitude of that is square root of 0 squared plus something squared, which becomes something. All right. So I end up with this. Okay. So if I think about this, let's say, I want to turn this is basically what we're going to start thinking about next, right? Let's say Vn was a sine wave and I don't know its frequency. And I just want to think about, okay, what would happen if the frequency of the sine wave at Vn changed? Right. So in other words, let's say I hooked it up to one function generator and I changed the frequency of the function generator, right? What would happen as the frequency got higher? The magnitude would get smaller and smaller and smaller, right? At DC, it would be infinite. At 1 hertz, it'd be pretty big. At 10 hertz, it would be smaller, all right? At 20 hertz, smaller, 100 hertz, smaller. This circuit is something that I would call ultimately a low-pass filter, because what it's doing is it's gonna make low frequencies go through, and a really high frequency would effectively be equal to nothing. I wouldn't get anything at the output if I had a really high frequency. Now that thinking is what we're going to learn over the course of the next 2 weeks. All right. But so I don't expect you to fully appreciate that today. What I do is the last time I'm going to talk about op amps as op amps. I'm going to use them in circuits from this point onward. All right, but last time I'm going to talk about op amps specifically. Then we're going to get into this notion of filters, which is how do I actually look at certain circuits to keep certain frequencies and get rid of others? Okay, which is pretty common to do, you know, in all sorts of different reasons. But when you're, you know, interfacing with a microcontroller or something like that, pretty common to do. All right, so I will